We're going to do a couple of practice problems so you can see how these equations are used, and then we're going to go to a worksheet with some more problems. Our first example is to calculate the delta G standard for this particular redox reaction, Cu2 plus Fe going to Cu plus Fe2 plus. I'm leaving the states off of this just to make it easier to write. So calculate the delta G for this reaction. Because I can see that this is a redox reaction, and the way that I see this redox reaction is that I can see I have ions that are changing in their charge, or atoms that are becoming ions, ions that are becoming atoms, and that is a characteristic of a redox reaction. So I know that this is a redox reaction, and when I'm calculating the delta G for a redox reaction, I'm going to use negative NF cell. So in order for me to be able to use this equation, the very first thing that I need to do is calculate E cell. Or that's the first thing I want to do, at least. And remember that E cell is the cathode minus the anode. And normally we would say that E cell is always a positive number. And that is definitely a true statement when we are talking about a galvanic cell. So if we're putting these two half reactions together and allowing the electrons to move in whatever direction they want to move, then E cell is definitely going to be a positive number all the time. But when we are looking at a specific balanced equation and nobody is using the word galvanic cell, we don't know for sure that this reaction is moving in the spontaneous direction. It might be, but it also may not be, which means that we really can't rely on just finding the answer, the subtraction, the combination that gives us a positive E cell. It may not always be positive unless we know for sure that we have a galvanic cell. So that means we're probably going to have to think a little bit more. What's the cathode and what's the anode? So before we get into the E cell, let's break this reaction down into its half reactions. We know that we have copper, and it's going copper 2 plus to regular copper. And then we also know that we have iron going to the iron 2 plus ion. And remember that this is not easy or not hard to fill in the electrons, but we don't have to do that from using our brains. We can go to our table of half reactions and we can find these reactions on the table, which we're going to need to do anyways because we need to know the voltages of these half reactions. So I am looking through, I have the one that's not in alphabetical order. Here is our copper half reaction. This is the correct one. We have to be careful that we find the correct one. And then same with the iron, we need to be careful to find the correct one. So here's our iron half reaction. And there's the voltages that we want to use. And this also gives us, if there are any parts of the half reaction that are missing, it's going to give us the parts of the half reactions that we need. So let's switch back and let's fill in those half reactions, fill in the electrons to the half reactions. And then let's also go back to the table and get the voltages of those half reactions. So the copper voltage is 0.3419. And the iron voltage is negative 0.447. And before we plug into E cell, we want to make sure that we know for sure which one is the cathode, which one is the anode. Remember your tricks. You have red cat, which tells you that the reduction is taking place at the cathode, and you have oil rig, which tells you Reduction is gain of electrons or adding electrons. So here's where we're adding electrons. So this is our reduction, and this is our oxidation. Oxidation is loss of electrons. And so that means that this is our cathode, and this, I didn't leave a lot of room for myself, this is our anode. So now we have the information we need to calculate E cell confidently. Cathode minus anode is going to be 0.3419 volts minus negative 0.447 volts. So this one is set up to move in the spontaneous direction like a galvanic cell. But like I said, you know, you can't trust that it's always going to be going in the right direction. You definitely can't trust Alex to not give you one that's backwards. So there is our E cell. So there's our voltage. So we have, going back to our equation, let's not forget what we're trying to do. We're trying to calculate delta G. And so we have figured out the E cell part of the equation. I don't know why I wrote it out there. We know what it is. It is 0.7889 volts. So now let's tackle N. N is the number of electrons that are exchanged when the equation is balanced. In this particular example is not great for illustrating that. In general, you don't want to just look at the electrons in any particular half reaction. You want to think about, if I was going to combine these two equations together, what would the stoichiometric coefficient of the electrons be? In this case, it happens to be 2, the same as what we have for our half reactions, so that works out pretty nice. So N is 2. F is Faraday's constant, 96500 joules per volt times mole. And then we're multiplying by our volts, 0.7889 volts. So the units of volts will cancel. N is, just to be clear, N is the number of moles. And it is a unitless number when we're plugging it into this equation right here. So this particular mole unit does not cancel. It stays intact, and that's good because the units of delta G are joules per mole or kilojoules per mole. So we need that unit there. And so let's work the math out on this. -2 times 96500 times 0.7889. We get a pretty big number. So I'm just going to immediately convert it into kilojoules. -152 kilojoules per mole. Remember, to convert from joules to kilojoules, you're just going to multiply by 1,000.